Transmission line is characterized by having a certain amount of resistance that's distributed along the line and some inductance, and then we show some shunt capacitance also present, and then this is repeated because the distribution of the parameters goes on, and usually the resistance is given in terms of ohms per mile, inductance henries per mile, capacitance in terms of farads per mile. And so the typical line would look RLC, then it tends to repeat every so often. Now, resistance is given normally by rho times L over A, where rho is resistivity, L is the length of a piece of a conductor, and A is the cross-section area. Very often in transmission lines we'll talk about R over L being simply rho over A and call that the resistance per unit length. Similarly, the inductance is often specified as henries per unit length, and the exact formula would depend upon the type of material, whether it's non-magnetic or magnetic material being used for the inductance. Let's talk about resistance just a minute. We'll talk about inductance capacitance later. In the case of resistance, we're very accustomed to seeing a circular cross-section conductor which has a cross-section area A. This is the A that appears in this equation. And at DC, it's a fairly simple thing to calculate the resistance per unit length or the overall resistance of a piece of conductor. However, at AC, it becomes a bit more challenging because the phenomenon observed is this. When AC current is flowing in a conductor, instead of flowing into the board or out of the board as the case may be and using the whole cross-section area, it tends to travel around the edges so that the electrons are in this outer ring and they're moving out or moving in on the conductor. The higher the frequency of the signal, the thinner this ring becomes and starts moving out more towards the edge. And as the frequency starts to drop, the ring starts to move in towards the center, and eventually as you approach DC, it comes back to this picture. This distance between these two rings where the conduction is actually occurring is called the skin depth. S-K-I-N-D-E-P-T-H, and the skin depth is given by a simple formula delta, and delta is equal to 1 over the square root of pi times F times mu divided by rho. Pi we're familiar with, F is the frequency, mu is the permeability of the conductor, and rho is the resistivity. And to give you an idea how some of these numbers would turn out, for copper, for example, for a piece of copper, for which we know things like the permeability and the resistivity, if we were to put those numbers into this equation for skin depth, we would find that delta for copper turns out to be 0.066 divided by the square root of F meters. Now, just to put it in perspective, let us try some different frequencies and see how big this skin depth turns out to be. Incidentally, we very often get away from meters and like to use mils as our units instead of using meters. And to make the conversion, we take the number of meters that we have and we multiply it by 10 to the 5th over 2.54. And that converts meters to mils. So if I do that for our problem here and just convert this by multiplying by 10 to the 5th over 2.54, and I try, say, 60 hertz, and then I'll try 10 megahertz, or I'm sorry, 10 kilohertz, that's 10,000 hertz, or I could go up to 1 megahertz. Here's some of the values you will find for skin depth. Delta up here is about 336 mils. At 10 kilohertz, it drops to about 26 mils for the skin depth. And at a megahertz, it's about 2.6. 2.6. Notice as you go from 10 to the 4th to 10 to the 6th, we change by a factor of 10 because of the square root relationship involved in the frequency expression. So, at 1 megahertz, this piece of copper will have the current concentrating in a very thin ring around here that's only 2.6 mils deep.